Good morning, everybody, and thank you all for coming. My name is Mark Blanchou. I'm a security consultant for ISEC Partners, which is part of the NCC group. So I'm here to talk to you about race conditions introduced by the compiler and the hardware in log-free code, which can be observed in parts of OSes and VMs, among other applications. So we don't have too much time, so I'm going to start this thing off with the problem. The problem is, and it's probably known by most of you, but the compiler does not create a binary that will execute the code you write. What you write is expensive and not optimized, so a different program is usually compiled instead. It is the same at runtime. Your hardware can do optimizations, such as instruction reordering, which should not be visible to a single thread, but can create issues with not properly synchronized code running on more than 2 cores. So why should you care? Log-free code is used for parts of several types of applications, and we'll see why. But writing that type of code is hard. And since finding these types of bugs have not been told too much in the security industry, there are still a lot to be found. And this applies to several layers, from compiler to hardware-introduced bugs, as well as wrong assumptions developers make about memory models in various languages and platforms. These bugs are relatively tricky to find and easy to miss because they can be introduced in code that could be assumed to be correct and not show at all during testing. But they can appear when certain conditions are met, when the code runs on a different hardware, or even when it's compiled with a more recent version of a compiler. So I'm not going to disclose any bugs during this talk, but I will give you some of the information you need to be able to find bugs that can potentially have severe consequences, since some of them can potentially lead to or help into finding privilege escalation vulnerabilities. So I'm not going to go into too much details in regards to definitions related to the hardware or the compiler, but I'll try to cover information that would help you better understand the problem. I will then discuss various issues that could be introduced by the hardware and the compiler in log-free code. I will later on explain some techniques that can be used to find these bugs. So what are logs? When you share data between threads, you usually see the use of locks. They were first created because of the difficulty in writing multi-threaded programs. With them, you don't have to worry about reordering or some optimizations, and they are getting faster than they used to be. Okay, so this picture is kind of intense. Don't get me wrong here. Locks are good. But they are kind of like this tank. Pretty strong, relatively slow, safe, but can also get your program stuck. Okay, so what is log-free programming? By definition, it is impossible for the system to lock up when you're using log-free code. So no more deadlocks when your program gets stuck, or live locks in cases of resource starvation. So suspending a thread, for instance, will not block the entire program. We use it for real-time operations, multimedia, financial apps, OSs, VMs. We use it for interrupt handlers in real-time systems, or when tasks have to complete within a certain time limit. It also has scalability benefits on multiprocessor machines, and it's usually faster than logs when written correctly. So let's start with the very obvious. What does the compiler and hardware know when compiling or executing code? They just know what's going on within a single thread. And they obviously don't know about any memory location that could be shared across threads. So the same thing, it is the same thing than when writing logs. You have to let the compiler and the hardware know. But you can't make assumptions about memory models anymore, like thinking the CPU doesn't do anything that can break this, so it's okay. Now you have to use the appropriate barriers and understand memory models of the compiler and the hardware. So two of the main concepts to understand here are cache coherence and sequential consistency. Cache coherence means that writes made by a processor are eventually seen by other processors without being lost or overwritten. But you should not really have to care too much about this, since the OS, the compiler, and the hardware should make sure it is true. But sequential consistency is really important. It is language and hardware dependent. It basically means that in a perfect, sequentially consistent world, the program you write is executed as you wrote it. So it means that they should not reorder instructions all over the place, which they do anyway, but this reordering should not be visible. So sequential consistency in current hardware and languages is kind of an illusion, even though you should be able to force it to some extent, but it would be very slow. So let's talk about compiler specifics. In addition to potentially reordering what you write, it can do a lot of other optimizations. And it does that assuming the code you write runs on a single thread if you don't tell it otherwise. In addition, there are things like profile-guided optimizations or even add-ons to compiler to obfuscate the generated code you write that can potentially create other issues. But I'm not going to talk about them today. So memory models tell you types of reordering that can occur depending on the code for the compiler and the generated binary for the hardware. Again, this is specifically important for log-free programming. They are basically weak and strong memory models. Weaker memory models are further away from sequential consistency and allow for the most aggressive reordering. In the loosely ordered category, we have ARM, which is used for mobile and tablets. We also have Itanium, which is used by enterprises, and which is a bit scary. And we have all of these software memory models, depending on different types and function you can use for your programming language. So let's start with the reordering issues. So reordering can happen at runtime and compile time. Let's see. All right. So I'll detail some of the potential issues that can be very exhaustive. So I'm not going to be very exhaustive due to a short time frame for this presentation, but I will mention some of them within this part. So as I already mentioned, this is not a problem when you use locks, but that can only mostly appear when you use lock-free programming. I'm going to start with atomicity. So one critical component for multi-threaded programs is atomicity. An atomic operation means it occurs instantaneously, and it basically prevents other threads from interfering when modifying a memory location. C and C++ operations are not presumed atomic, even though some native types can be if they are not wider than the memory bus and if they are aligned. So, for instance, non-aligned read or write, like the example at the bottom here, or an operation that read or writes more than 8 bytes on a 64 bits wide bus, for instance, are probably not going to be atomic. Another example of non-atomic operation is a simple incrementation with actually 3 instructions: a load, an increment, and a store. So this cannot be atomic. To be atomic, you need to either use the atomic keyword C++11 and use read, modify, write operations that usually allow performing several basic operations that will appear as atomic. So let's take an example of compiler reordering. The code at the top generates machine code as it writes. This is compiled without any optimization flags on G++. So I basically set a value to a global variable in the first thread and use another global to tell the second thread that the variable is updated. So as you can see, this is compiled more or less as I wrote it. In the code at the bottom of the slide, I use the -03 compiler flag with G++, which tells the compiler to optimize the code. And you can see optimizations and reordering in that case. You can get a better picture of the problem here. The second thread uses the global isUpdated variable to retrieve the content of the global value variable set by the first thread. By reordering the instruction in the code of the first thread, the second thread can get an incorrect value for the global value variable. Now I'm using a compiler directive to prevent reordering. And as you can see, this is not reordered anymore by the compiler. But it doesn't mean the CPU is not going to reorder this, as I use the compiler-only barrier. But I will talk about that later. So I listed here barriers that should be used to prevent compile time reordering. Some of them are specifics, such as the interlocked operation or C++ atomic types, which should be the best things to use here. Some of them are also implied to be compiler barriers, such as most of the hardware barriers, as well as some function calls. Even though some of them are oftentimes inlines, so you can't really effectively rely on that. You may need to use a compiler directive for forcing it. So it is, okay. So developers oftentimes use the volatile keyword as a compiler barrier, but this is not atomic, and it's kind of implementation dependent as well. So it's not really recommended to use it for synchronization purposes. So this volatile keyword is completely different from the one used in Java or .NET. As the one used in Java acts as the C++ 11 atomic type, which is a full memory barrier. So let's talk about hardware reordering. There are a number of guarantees one CPU has to provide for a single thread to appear sequentially consistent. The main one is that dependent memory accesses are done in order, which makes sense. But it is not a guarantee that independent loads and store are done in order, which again is fine for single-threaded code, but can create issues if more than one core is involved. This reordering is also dependent on the architecture and will be more or less aggressive depending on its memory model. For example, even on x86 64 CPUs, which have a strong memory model, it is allowed to delay a store past any loads from a different location, which can create various issues. So the compiler needs to use the exchange instruction for a store instead of a move, which is then a full memory barrier and is needed to prevent reordering. So I listed here some hardware barriers that would prevent runtime reordering. Most of them also act as compiler barriers. So there are actually a lot of different types of barriers depending on the CPU and its memory model. But compilers usually agree on instructions they use for the different barriers. On x86, for instance, the sequential consistent store I talked about earlier is almost always an exchange, and not an mfunds plus move, as you can see on this documentation, which could work too, but the exchange is actually cheaper. As you can see for ARM on the right, there are a lot of different instructions depending on the operation, because it reorders way more aggressively than x86. Now I'm going to talk about some optimizations compiler can do and that can create issues in log-free code. This slide lists some optimization that can be bad. I won't talk about them in details, but I will show some examples. So what can go wrong here? Any idea? All right, so in the first thread, you could get a potential compiler and CPU reordering, as discussed in the previous slide. In the second thread, the compiler is likely to do a register promotion, which means it is likely to load the global done into a register, which is a completely valid optimization, but won't work in a multi-threaded environment. And this is a relatively obvious optimization, and a developer would see the problem pretty quickly if that happened. So let's use another example in the context of the kernel. The double fetch, or time of check to time of use type of issue, is kind of a classic race condition that can potentially lead to privileged escalation issues in kernel code or in VMs, for instance. So it basically happens when there are two memory reads in kernel space from a user writable address. You can see that in ioctl handler's code, for instance. The first time the memory is fetched, the kernel code validates the value and then uses it. But when it is used, it's fetched a second time from user space memory, which can be controlled by a low privileged user at that point, and can then effectively lead to memory corruptions or other various issues. So this is a very raw example. This could be the code in a ioctl handler, for instance. The P user space memory pointer points to attacker-controlled memory in user space. Probe for write validates the memory to make sure it is in user space. And the same pointer is then used to copy data from kernel space, for instance. In this case, the attacker can modify the memory containing the address of the buffer and its length. And this can be done after the probe for write check, which can then lead to writing into kernel memory. So, as a mitigation, we could capture the data structure containing the buffer information, and we could be fine in theory. And that's what you can see in a lot of kernel code sometimes, or drivers. However, in this example, the compiler could potentially optimize the code capturing the data. It is always legal to reduce the set of possible instructions. And we could get the same double fetch issue that could easily go unnoticed. Now, if you apply a compiler-specific mitigation here to force the capture of the variable with a cast into a volatile type, we can potentially do that because we don't need atomicity, and memory accesses are performed in order here. But in the case of a compiler bug, which can happen, the data would still be captured twice. So again, log-free code is hard, and not only to application developers, but also to people writing compilers. Compiler bug exists, and they are more frequent than you may think. And this can potentially impact a lot of code that will probably never be recompiled again. So it is relatively tricky to find these bugs, but finding out which version of the compiler was used, as well as knowing bugs a specific compiler can introduce, could be a start. Looking for specific instructions would allow you to find code sections that should be protected. Then you need to determine if the right hardware barrier was used everywhere, and this mostly works for weaker memory models. You could use a thread sanitizer or TSAN, which is based on Valgrind for Linux and macOS, and PIN for Windows, which is a dynamic binary instrumentation tool. Also, if any double fetch has been introduced, Drew and Ginvail are going to talk about a tool to find that kind of issues more easily tomorrow. So if you have the code, you should make sure you understand well all of the various memory models and thoroughly test code that should not be optimized in any way. If you are a developer, you should consider using LUKS where you can if you're unsure about some of the memory models of the language. In terms of testing with the code, you should probably write as many test cases as you can and use a thread sanitizer. You could also do equivalence checking using different compilers, but it could be pretty difficult as you need to write, you need to know which generated code is supposed to be correct. Testing with CPUs with weaker memory models can be good as well. You could cross-compile for Athenium, for instance, which is a weakly ordered CPUs, and see if the code still works fine. So all in all, log-free programming is hard. It can introduce tons of issues in the applications you are testing, even in otherwise correct code due to potential compiler issues. All right, thank you.